Let me start by introducing Phil and thank everyone for coming here today, for joining this session. I'm very happy to introduce Phil Kaaret from NASA Marshall Space Flight Center. The title of today's talk is Results from Imaging X-ray Polarimeter Explorer, IXPE in short, with a focus on gamma ray binaries. Phil, I think everyone knows Phil well. He's an astrophysicist at the NASA Marshall Space Flight Center. He's the PI of IXPE. Phil got his PhD from Princeton University, and since then he's had a long career in astrophysics. He has served as faculty at Columbia University, at the University of Iowa, and when he was at the University of Iowa, he was the PI for Halosat, which was the first CubeSat mission, and has been flown by NASA SMD. And while at Columbia and then also at the Harvard-Smithsonian Center for Astrophysics, he was the project scientist of the Stellar X-ray Polarimeter. Phil's also been a colleague on Veritas, and I've worked with him personally, and it's been really a great pleasure. So let's welcome Phil today and get started. As you know, the format of today's talk is 50 minutes for the first part and then questions. And then I hope we can continue discussions beyond those, the first hour. So thank you very much, Phil. And I hope you can keep coming to these seminars. We hold them every 2 weeks on Wednesdays.
Okay.
So let's get started. Thank you.
Okay. Thanks for inviting me, and everyone can see the slides. Nod your head, Griffin. Okay. So I'll go. And it's nice to see a bunch of old friends and a bunch of new people. And here's the title of my talk. And the body of the talk will be on SS433 and B1259-63. So I'll start with a introduction to polarization. I mean, we're going to talk about X-ray polarization in particular. But so polarization has been it's actually described by someone at our recent NASA senior review as the holy grail of X-ray astronomy. I'm not sure I would go that far, but it's a vector, or really it's a direction, since it's modulo 180 degrees, which intrinsically measures geometry. If you measure the polarization of some source, you find out something about its geometry. And so I'm going to be talking a lot about the electric vector position angle. IXPE only measures linear polarization. And so what we really do is measure the orientation of the electric fields of the X-rays that are coming in from the astrophysical source. And so I've listed a few physical processes. In polarization, what we really can do is tie back the polarization to how the photon was produced. And depending on how the photon was produced, that tells us different things about the geometry of the source. So if we have scattering or reflection, and that's the figure over here, and can people see my mouse when I move it around?
Can you try again? I don't see it.
Over here. Wow, okay, unfortunate. So if I go to the right figure over here, you see a source of photons, and then the yellow thing is a scattering target. And depending on the angle, you will have a highly polarized beam if you scatter through a large angle, a near zero polarized beam if you scatter in the forward direction. But if you have scattering, the EVPA, the electric vector of the photon, has to be perpendicular to the scattering plane, as you can see. So that immediately tells you if you have a polarized source, you can tell the plane in which the scattering occurs, and we'll do that later on. If you have photons that are emitted by synchrotron radiation, the EVPA tells you about the magnetic field lines. If you have strong magnetic fields, like around magnetars or other highly magnetized neutron stars, you'll have different opacities, parallel versus if the electric field vector is parallel versus perpendicular to the magnetic field as the photon propagates. And that can tell you about the configuration of the magnetic fields of the source. And if you have strong gravitational fields, the EVPA is parallel transported along the space-time geodesics, and that actually enables you to even constrain the spin of black holes using polarization measurements. So this is an image of a drawing of the Imaging X-ray Polarimetry Explorer, or IXPE, or if you're Italian, it's IXPE. And the key things are at the top center, we have 3 telescopes. Those were built at Marshall, the so-called mirror module assemblies. And then down at the bottom right of the figure, we have 3 detector units. And those are the polarization sensitive detector units. And that's really the technology that's enabled IXPE to go ahead now. And so IXPE is a collaboration between NASA and the Italian space agencies. The Italians built the polarization detectors. The Marshall Space Flight Center built the mirrors, and then NASA paid for the spacecraft and most of the operations. The Italian Space Agency also provides our ground station and a lot of support to the Italian science community. It's a so-called small explorer, which is the budget for construction in the first 2 years of operations was $188 million. It was launched in December 2021. Science observation started in early 2022. So we're in our third year right now. The energy range is the old standard X-ray energy range of 2 to 8 kV. And the detectors, which I'll get into in a minute, are actually gas-filled proportional counters. So the energy resolution, those of you who are old X-ray astronomers would be familiar with this. It's a factor of several worse than the standard, the CCDs, which are standard for instruments now. And the field of view is about 10 degrees, and the angular resolution is not too bad. It's 30 arc seconds. And so the way IXPE actually works is to measure X-ray polarization via the photoelectric effect. So the idea is we have these detectors, again, built by the Italians, that are filled with gas. It's actually dimethyl ether. And so an X-ray comes in and interacts with one of the molecules in the dimethyl ether. And you can actually think of it as the electric field vector of the X-ray pushes a photoelectron out of the molecule. Okay, so that's our primary photoelectron. And the initial direction in which that photoelectron is emitted is it's determined by the electric field according to that sine theta cos squared phi distribution shown over there. So what we really have, so what IXPE does is the gas per pixel detectors built by the Italians essentially take a picture of the photoelectron track for each X-ray that comes in. And one of those pictures, actually the very first one from an astrophysical source detected by IXPE, is shown on the right-hand side there. That's actually a photoelectron track from Kaaret, the photon energy about 2.7 keV. And what we have to do from that is reconstruct where the X-ray interacted, what its initial direction was. Okay, so what makes this difficult is that the photoelectron doesn't follow a straight path. It actually does lots of scattering in the gas, and it actually deposits more of its energy at the end of the track where the photoelectron is losing energy, at the beginning of the track where it had the maximum energy. And so the color in that figure is actually proportional to the amount of charge deposited in each of our hexagonal pixels. And you can see the green spot is actually where we think the X-ray interacted. And then the photoelectron actually moves away from the green spot and deposits most of its energy at the end of the track. And what we have to do is reconstruct that initial direction, which is shown by that green line. Okay. So that'll actually be all. Well, I'll get back to technical results at the end, but that's all for now. So science results, IXPE has made observations of a whole range of different objects: blazars, neutron star, low-mass X-ray binaries, accreting X-ray pulsars, accreting stellar mass black holes, supernova remnants, pulsar wind nebula, magnetars, radio quiet AGN, the center of our Milky Way galaxy. We actually did make an observation of a gamma ray burst, the so-called brightest of all time burst. I won't talk about that. And then we recently transitioned to a general observer phase, where anyone in the community can propose targets. And from that, we've been adding new targets, accreting millisecond pulsars and a radio galaxy and extended jet. And actually, in the most recent cycle, we also added an observation of a cluster of galaxies, the Perseus cluster that we're just doing now. But IXPE's really opened a new window on the cosmos. We have new results on the magnetic field geometry and acceleration zones and that variety of sources. We have new results on the accretion geometry near black holes. And then also new results on the behavior, matter, and strong magnetic fields, new neutron stars. And we're really making exciting discoveries. So I'm just going to go over a few of these fields quickly. I see actually from your program that you have a bunch of IXPE talks, including one by Henrik later on. So I'm, except for the gamma ray binaries, I'm going to leave most of the details to those talks. In fact, a couple of topics I'm going to skip over in favor of time and just touch a few of the highlights. So one of our big results is actually on the geometry of the corona and accreting black holes. And so the spectra, the X-ray spectra of black hole, of stellar mass black holes, reveal two main components: a disk component, which is a thermal thing, and then a corona, which is a power law or a Comptonization component. And these have been known for decades, literally since the 70s. But the decades of spectral and timing observations have been really unable to determine the geometry of the corona. But the first IXPE black hole observation of Cygnus X1 found the polarization was aligned with the jet. And the figure in the middle of the plot's actually from Henrik's paper that appeared in Science in 2022. The orange, the line and the sort of the yellow and orange bands are the uncertainty on the polarization direction, and the contours are a radio image. So you can see that the EVPA is well lined with the radio jet. And that means, if you just think about that picture that I showed you before, and I'm showing you again about the scattering geometry, it means the corona is extended along the disk. And if I then go to the top, this excludes some models. If you look at the image on the upper right, it actually, this is a commonly used lamppost or base of a failed jet model for a corona. And it's vertically extended, and that's incompatible with the IXPE results. And so we're really making progress. I mean, you know, science really progresses by falsifying models, and IXPE pretty effectively falsifies this model for the geometry of the corona in favor of the model towards the center of the page, where the corona is actually extended along the accretion disk. And again, for more details, I see that Yuri Putinen is going to speak in March, and then Henrik will speak in May on the results of these sources. Okay, so I'm actually not going to quite leave black holes yet, but IXPE observed Swift J1727 8 times. This is a transient that went off in 2023 during the PRIME mission, and then actually stayed bright until the first cycle of the general observer phase. And you can see over on the right side, there's the hardness intensity diagram. So the X-ray hardness in those particular bands is plotted on the horizontal axis. The photon flux is pointed on the vertical axis. And the IXPE observations are marked with stars and numbered in sequential order. And you can see how the source evolved at the standard Q diagram. We didn't catch the rising hard phase. We caught when it was quite bright in the hard phase. It decayed down towards the hard intermediate phases. Observations 6 or 7 and are in a soft phase. Unfortunately, the source was not visible with IXPE when it was in the bright soft phase, and then it evolved back over to the dim hard phase in observation 8. And so the observations, the plots in the middle of the page actually show the polarization degree PD and the polarization angle, or what I'm calling in the other slides, the EVPA, as a function of the X-ray hardness. And so you can see that there seems to be a trend of decreasing polarization with decreasing hardness. And then when we go into the soft state, we get only an upper limit. So really in observations 1 through 5 and 8, the emission's dominated by the corona. And the striking thing about this is the dim hard state observation number 8 lies on exactly the same trend as the bright hard state observations, even though there's a factor of 100 change in flux between the two. And we can reproduce this with existing models, but it kind of requires fine tuning of the parameters. But it seems to be a very robust result. I mean, the accretion geometry is essentially the same, even though there's this huge change in accretion rate. And it really is a good question of whether that points to something fundamental. Okay, and then IXPE has now actually acquired enough observations of accreting black holes that we can do a population study. And such a study was done by Linny Sade, who's a postdoc here at Marshall Space Flight Center. She's actually applying, she's in her 2nd year and applying for jobs. And if any of you have a position, I do recommend her for the position. And over on the plot, you can see the polarization degree plotted versus the compact object mass. And there's, of course, the cluster at the stellar mass and then the cluster at the supermassive. But you can see the basic range of the sources doesn't seem to, we have some sources with high polarizations, both the stellar and supermassive cases. And we have a band of polarization. The blue points identify sources in the hard state, like showing you on the previous page. The black sources actually identify sources in obscured, where the central object is obscured. So there's no strong dependence on the black hole mass, which argues for independence of the accretion geometry on black hole mass. The more interesting plots over here. So what Linny did was take the polarization angle and measure the offset from a symmetry axis. So you can think of the symmetry axis basically the jet axis. And some systems, they don't produce jets, so we had to use something else like an ionization cone to estimate the symmetry axis. But the idea, you can think of it as just, is the polarization angle offset from the jet axis, or the source to make a jet. So you can see that the polarization degree is large, tens of percent when the offset's near 90 degrees. That actually fits very easily with the picture I showed you of Thomson scattering before, where you expect large polarizations. And those are the same sources that were obscured. And actually, that's a mix of Cygnus X3 and a couple classic AGN like NGC 1068 known to have obscured central sources. Okay, and you can see also that the hard points cluster together. So the circles are stellar systems and the squares are supermassive systems. And you can't tell, the cluster of blue points down at polarizations of a few percent. Those are all systems where the emission is dominated by the corona, what we call the hard state. And you can see from that supports the idea that stellar and supermassive black holes share a common coronal geometry. The polarization degrees and their angles relative to the system axis are just the same. Okay, and the large polarization for the obscure systems actually also supports the AGN unification hypothesis. Now I'm going to switch topics. One of our interesting results that was published last summer in Nature Astronomy is on Hercules X1. It's an X-ray pulsar, has a spin period of 1.2 seconds, an orbital period of 1.7 days. It has a stable superorbital period of 35 days. There's been a long-standing question of whether that superorbital period is likely due to precession, but is that precession of the accretion disk, or is it of the neutron star itself? So with IXPE, what we can actually do is do pulse phase resolve polarimetry. And so that's what's shown in the upper panel there. And so what we can measure is the polarization angle versus the pulsar phase. And that actually, using a rotating vector model, essentially it's a dipole rotating around, it enables us to measure the geometry of the magnetic field and its relation to the neutron star rotation axis, and actually the inclination of the rotation axis to our line of sight. And from that, for the very first time, we can actually see the neutron star in Hercules X1 precess around. Okay, so these different states, or you can see the 35-day superorbital period has the so-called main on and short on states. And what we can actually do is see the neutron star progress as it goes around. So we really show definitively that the precession is due to the neutron star. It's not due to the disk. So that's exciting. A lot of exciting results have come out from measuring radio pulsars in great detail. IXPE, but accreting pulsars don't tend to be radio emitters. So IXPE really enables us to measure what the neutron star is doing, even when it's being accreted onto. And that will, with further observations, we actually hope to probe the interior of the neutron star and the coupling between the crust and the superfluid, something we can do because the neutron star has this accretion flow flowing onto it, something you can't do with isolated radio pulsars. Okay, so now for the rest of the talk, I'm going to talk about non-thermal particle acceleration. And in these cases, the X-rays will be made by synchrotron radiation. And so in the figure shown here, that's just a classic, it's from somebody's textbook. If you have a energetic particle gyrating around in a magnetic field, it moves in a helix and it produces synchrotron radiation, and the EVPA is perpendicular to the magnetic field. So from the direction of the X-ray polarization, you can get the direction of the magnetic field. From the fraction polarization, you can get the level of order. So if you have an extremely well-ordered magnetic field, you expect a high polarization. If you have a disordered magnetic field, you would expect zero polarization. In fact, the maximum polarization for synchrotron radiation is set by the distribution of the spectral index of the electrons, and I'll get back to that in a minute. So you're going to have a talk by Jaco Vink on March 12th. I'm not going to talk about supernova remnants. He'll do a better job than I would. You're going to have a talk by Alan Marsher on June 18th on blazars, so I won't talk about that. But I will briefly mention pulsar wind nebulae. If you guys need a talk on or interested in one, I would recommend Roger Romani to give a talk on pulsar wind nebula, and then the last part of the talk will be on TeV binaries. So one of the first IXPE results on a pulsar wind nebula was for the Velar pulsar wind nebula. And the real question here is, how are particles accelerated in the pulsar wind nebula? So Vela turned out to have a really high polarization, average polarization degree of about 45%. And in some regions, the polarization degree is above 60%. And for the spectral index of Vela, the theoretical limit for the polarization degree for synchrotron emission is 75%. So that's really close to the theoretical limit. That means that the magnetic field is very highly organized in those regions where we have the high polarization degree, and it's pretty well organized across the entire remnant. So we infer that we have a highly uniform field, and that means we have acceleration with little or no turbulence. If we have this is really evidence against turbulence-driven diffusive shock acceleration or any large amount of turbulence in the system, because that would drop the polarization degree. And so that really means that other processes like magnetic reconnection probably power this pulsar wind nebula and also others. Okay, so the Crab Nebula, actually shown here, we got the cover of Nature Astronomy back in May 2023, shows similar properties, but some slightly lower polarizations. And then our most recent result is the cosmic hand. If you hold up your hand, you can sort of see the pulsar is actually kind of in the palm of the hand, and then you have the fingers extended towards up that orangish nebula, which actually infrared image shows polarization up to 70%, again approaching the synchrotron limit in arcs near the pulsar and near the end of the jet down off to the lower left. Okay. So, well, I'll just point out that for this group, since pulsar wind nebula are good TeV sources, and I always think of this talk series as for TeV astronomers, that should be really relevant to taken into account going forward in the modeling of the TeV mission for the objects. So now I'm going to switch over to TeV binaries, and I'm going to start with SS433, and I understand the previous talk was about TeV emitting binaries and really focused on SS433, so I think you're all up to speed on the subject. I'll just remind you a little. There's an X-ray binary, which probably has a black hole compact object, though not completely clear, with a massive star. It produces inner jets really close to the binary on a few arc-second scale. The jets then reappear a couple of arc minutes out, about tens of parsecs outside. And I'm going to focus on this one, on actually the eastern jet. Shown here, there's the jet reappears in X-rays and then has a tail that goes off to quite some distance. So SS433 in X-rays and ultraviolet, the luminosity in X-rays itself is not notable. It's 3 × 10⁻39, which is like a standard neutron star low mass or the high mass actually X-ray binary sort of luminosity. But the source, of course, was discovered back in the 70s or early 80s with red and blue shifted hydrogen emission lines that showed the jets clearly contain hadrons and they're moving at speeds of about 0.27 C. The X-ray spectra also show blue and red shifted lines. This is actually a spectrum from one of Herman Marshall's papers on the source. The cross below iron 25 shows the rest frame energy, and the 2 diamonds show the blue and the red shifted peaks that you actually see in the data. And the kinetic power estimated from the jet is large. Herman estimates it about 3 × 10⁻38. Fabrica estimates it even higher, about 6 × 10⁻39. And the far UV luminosity, if you look at photoionized gas nearby and estimate how bright the central source has to be, how luminous the central source has to be, there's an estimate that the far UV luminosity is about 10 to the 40. So the binary is likely an ultraluminous X-ray source with an X-ray beam pointed away from us and accreting at super Eddington rates. So this is kind of a more detailed picture of a few different things. This is actually from Samar Safi-Hobbs' 2022 paper. Again, the binaries at the center as jets going out to the east and west. I'm going to concentrate on the eastern jet, and you can see there's a little dashed rectangle of a blow up of the central region where that eastern jet or eastern lobe reappears. And she took a new star image in the 3 to 10 keV band that shows the hard X-ray emission is really concentrated right towards the leading edge of where that eastern lobe reappears. Okay, and the hard X-ray spectrum is hard and non-thermal. The head also produces TeV emission, as we know from Lasso and Hess and Osohawk. And the head really is the particle acceleration site. So with IXPE, what we were interested in doing is, so this is from NuSTAR, we know where the particles are being accelerated. So what's the configuration of the magnetic fields in that region? Okay, so here in the upper right shows the IXPE image of that region. And so we're focused right on, we actually used the NuSTAR image to guide where we pointed, and what's shown as the head and the cone is the same as the head. Actually, the head and the cone come from Samar Safi-Hobbs' paper, that you can think of the head as basically circling the bright spot in the 3 to 10 keV NuSTAR image. And so we then took IXPE observation and we detected polarization. It's pretty strongly polarized. The polarization degree after correcting for the background is 17%, plus minus 4%, and the polarization angle, well, it's almost consistent with north. But the key thing here is the EVPA is perpendicular to the direction between the head pointing back towards the binary system. So again, for synchrotron, the magnetic field is perpendicular to the PA. So we infer that the magnetic field is actually parallel to the flow of the jet. And the maximum PD is 70% in this case for that particular spectral index. And therefore the magnetic field is well ordered, not quite as well ordered as well, actually, correction for the background, that the polarization degree is 50%. Sorry, I was reading the wrong number. So it's really highly ordered, even as highly ordered as the Vela pulsar wind nebula. So this raises the question, and then this is actually just a bit more. It's possible to do IXPE analysis either in a model independent way, that's the results on the previous page. You can also do spectropolarimetric analysis, which is shown here. For those who do X-ray emission, we actually use IXPE. The tools are exactly the same as anyone who's done analysis of X-ray data with IXPE before. It's actually, and I'll encourage this at the end of my talk, it's really easy to get into IXPE analysis if you know how to analyze X-ray spectra. All the tools are built in. And then from here, we can actually just find from IXPE also actually measure the spectrum of the source. Okay, so the key result here is that the field is parallel to the flow and the magnetic field is highly organized. And so the alignment is almost certainly due to velocity shear. You have this jet moving away from the binary system, and you have a magnetic field which is parallel to that jet. Okay, and it's sub-parsec scales in the inner jet that you can actually measure the radio polarization. It also indicates a magnetic field parallel to the motion of the individual knots. And you see a similar thing in FR2 radio galaxies, where you can see knots quite far out from the supermassive black hole. And that's probably really the analogous situation to SS433. And there in the radio, again, we see a magnetic field parallel to the flow. Okay, and so I'll actually go through a couple of possibilities for how the particle acceleration occurs. When I actually showed this to Roger Blandford, he said, oh, that's obviously reconnection. But it's also, it would also be possible to have shock acceleration at the shear interfaces. So a couple of the details here, just to get into more physical detail, the equipartition magnetic field is about 10 microgauss, which agrees with your talk from 2 weeks ago. The gyro radius is about 3 parsecs. That's actually a lot smaller than the transverse diameter of the X-ray emitting region. The bulk Lorentz factor, if you take the 0.26c, it's just about 1. And from those things we can, and then from Panferoff actually has a thing where he infers the jet density. If you believe that number, then the alphane Mach number is about 900, and the magnetization is 2 × 10⁻⁴, so it's very weakly magnetized. And here are just a few possibilities for how to accelerate particles. You could have a shock at the leading edge. In fact, the new star images really suggest that's the case, because the hard X-rays are hardest and brightest right at the leading edge of that lobe. And then you'd have synchrotron cooling downstream. So the alignment in that case would really be, this in the downstream region, not necessarily in the shock region. Okay, you could have acceleration at the shear interfaces. This has been suggested in a number of FR2 radio galaxies. It'd be of great interest to have any of the theorists on the call actually take the models proposed for the FR2s and see how they apply to SS433. In that case, you could have an extended acceleration region. And you could also have magnetic field reconnection in loops. I mean, if you generate loops in the shear flow like this, they will naturally recombine. This was suggested in a bunch of papers from the 90s and has been revisited more recently. And you would have continual reconnection events to produce a smooth power law. But that seems likely since the thing is pretty well extended. And again, in that source, you could actually have an extended acceleration region. Okay, so now I'm going to go on to the other TeV binary, which I'll talk about, which is PSR B1259-63. And this was, again, talked about a couple of weeks ago. It's a very famous source from the Hess results. It's young energetic pulsar orbiting a BE star. It's actually an O star with outflows. And there's TeV emission after the pulsar plunges through the stellar disk, which it does twice every 3.4-year orbit. Synchrotron emission was measured with the Aussay detector back on the Compton Gamma Ray Observatory up to 200 keV by Eric Grove. And it's thought to be acceleration at the pulsar wind termination shock. So again, we decided to go look at this. The last periastron passage actually occurred last summer. And it fortunately occurred during the IXPE observing window. IXPE observed after the disk crossing. And you can see here in the light curve on the bottom right, this is days after periastron. So we get the second disk crossing, which tends to be brighter in X-rays. And it has the SWIFT and the IXPE fluxes in the 2 to 6 keV band. And the dotted lines actually show the time of the IXPE observation. The dashed line shows the estimated time when the pulsar passed through the stellar disk. And we detected polarization at a lower level than SS433, 8%, plus minus 1.2%. And then the polarization angle was minus 42. But how do you interpret that polarization angle? Well, fortunately, 1259 has actually been observed with VLBI at the milli-arcsecond scale, and you can actually see the motion of the pulsar on the sky. And so that's what's shown by the black ellipsoidal curve on that plot. And periastron's marked, and then the start and stop of the IXPE observations are marked. And then the gold indicate the direction and then the error range on the EVPA from the IXPE measurement. And then the star is the center of mass. So you can see that the polarization is essentially aligned with the direction between the line running between the normal star and the pulsar. So the polarization, the X-ray polarization is aligned with the pulsar star axis. So that means the magnetic field is orthogonal to that axis, and therefore the magnetic field should be orthogonal to the shock axis. And so we find here that we're having acceleration in a perpendicular shock. And again, this is a situation where theoretical inputs would greatly, now that we have these results, it would be great to go back and look at models. Most people who've modeled acceleration in 1259 assume a completely disordered magnetic field. We now know there's at least some level of order in the magnetic field. So it'd be really interesting to take that into account. Okay, I'll also point out the evolution of the X-ray spectrum. This is actually a paper from Oliver Roberts here at Marshall, who was just submitted. He's actually moving to University College Dublin in September, so I hope you all welcome him there. And we obtained new star observations that covered the IXPE observation, and the spectrum is well fitted with a simple power law. Well, Up to 200 EV is from the Aussie case. With NuSTAR, we can go up to about 70 keV. And the plot shows the evolution of the photon index with time. This was actually already known from other papers, but we've added the data shown with the yellow kind of gold stars here. And it's interesting that we have a softer photon index right around periastron, and it gets harder as we move away from periastron. This is probably because the energy loss timescale of periastron will be very short, since the stellar photon field there is very strong, and as we move away, that field, 1/r² gets weaker. And also, Oliver pointed out that the hardest spectrum actually aligns with the start of where GeV flares are aligned. So that's would be an interesting thing to think about, and also it would actually be interesting to get more NuSTAR data to cover that range better. And also from the IXPE results, we have a kind of marginal 99% confidence level result that suggests that the polarization degree is actually much stronger in the first half of the IXPE observation, and then goes down to 0 at the end of the IXPE observation, which would suggest the magnetic field becomes less ordered as time goes along. Okay, so that's actually pretty much the end of my talk. I'm just going to plug, since I'm the PI of IXPE, one of my jobs is to try to increase the community. So we do have a general observing program. It's free to people across the globe. The next deadline will be September 11th, 2025. We have, we have joint programs with NICER, NuSTAR, and SWIFT. We're actually adding a joint program with GRISM, and we've already added one with the National Radio Observatory. So for any of those 5 observatories, you can write an IXPE proposal and also get time on one or more of those. And if any of these results are of interest to you, please propose to the GEO program. Lots of, especially if you have new ideas of targets we haven't observed before, but that's really how we keep the mission going, is to have a healthy general observer community. And also, you can analyze IXPE data yourself. All the IXPE data from the prime mission and the majority of data from the GEO program are public. By default, IXPE has no exclusive use period, as NASA headquarters likes to call it. We actually happened after NASA headquarters went into a very strong, all data should be public mode. And so you can request an exclusive use period up to 6 months. I do suggest that. If you do propose to the GEO program, you can just, check a little box saying you want up to 6 months exclusive use, and you have to write a short justification. If you just parrot one of the if you have a student working on it, you'll get your exclusive use of 6 months for sure. All the tools for IXPE analysis are publicly available. And as I mentioned before, the tools are very familiar. It's all inside of the HEASOF packages. So if you've ever analyzed data for NICER, NuSTAR, or SWIFT, you actually know everything you need to do. You just need to substitute a few specific IXPE tools, and then most of the analysis itself is done in the XSpec package. XSpec was actually modified. It was extended in order to handle polarimetric information. And so you can, but from the user point of view, it's almost the same. You just have a couple more spectra for the Stokes Q and U parameters. And then we have a quick start guide on the HEASOF IXPE pages in order to get people started. Okay, so that's it. I just want to say thank you from the IXPE team. These are just a few pictures. It takes a lot of people to build such a mission. Our critical design review is shown in the bottom right over there. The 2 original PIs, Martin Weisskopf and Paolo Safita from Italy, are shown in the middle panel on the top, winning the head Rossi Prize at the recent AAS meeting. And then and the other pictures, the mission's actually operated by a bunch of students out in Colorado, shown in one of the pictures. Then we do some public events. And I'm going to summarize my science results on this over here on the binaries. For SS433, the magnetic field is shown in the dashed lines. It's parallel to the jet flow, while in 1259, the magnetic field is, and in SS433, it's well highly ordered in magnetic, but in 1259, it's actually perpendicular to the field there, the direction of the flow, and it's less well ordered. So thanks very much, and anybody have any questions?
Thanks. Thanks a lot, Phil. That was great. So questions. See some hands.
Let's see. Okay, we got a couple. Evgeny, you're first, I guess.
Thank you for the presentation. My question is, if I'm correct, then in one of your slides, I have seen magnetization something like 10 to the minus 4 for the jet, for the microquasar jet. Then is it enough, if you have such a low magnetization, is it enough energy in the magnetic field to power acceleration? Once you're talking about reconnection, you cannot get more than you have in the magnetic field, right?
Yes. And I actually, that question occurred to me a couple of weeks ago, and I have not thought about it enough to actually have an answer, but I'm not a theorist. I'm actually, as my old boss, Bob Novick, used to say, I'm much more of a plumber. But it is actually a really interesting question. I think that might be the key to distinguishing whether or not it's reconnection versus a shock. And then the magnetic field is just, if I go back to the two models here, that really might be a key way, because if the acceleration is occurring like Tavecchio, sorry about the pronunciation, suggests the energy would come from the shock, and you only need the magnetic field to become aligned downstream of the acceleration. You don't need it to accelerate the particles. And I think that's a really good consideration to conclude whether or not you have enough emission there. The reason that it might be reasonable is that the X-ray luminosity is quite low. If the jet power is really something like 10 to the 40 ergs, you only need a small fraction of it to actually produce the observed X-ray luminosity, which I think I had on this page here. The luminosity is something like 10 to the 34. So it is a really interesting question, because that luminosity is so much lower than the jet power. It might not be enough, but I think that's really an interesting avenue to go through to try to decide how the accelerations really occur. Excellent.
May I ask a question to Evgeny just?
Yes.
I don't understand why you think there is a direct relation of acceleration and the magnetization. I mean, if you go, energy goes to the relativistic particles. If you are talking about highest energy electrons, then yes, but otherwise there's no direct link.
It's because the question was whether it's a reconnection or not. If it's reconnection, then it's transfer of magnetic energy to particles energy. You cannot transfer more than you have.
Yeah, if reconnection, then yes, but generally it's...
Otherwise, yes, you are right, of course, I agree. Otherwise, there is no limit, yes. Thank you. I've got the answer. Thank you.
And then Oleg's next. Yeah.
Thank you for the very nice talk, Phil. So I find it very interesting, the result on Hercules X1 about the free precession and its period, because we have been looking at I work mostly with non-accreting sources. So we've been looking at some pulsars, like Pulsar Wind Nebula, which had a jet. It has a jet that is actually kind of like corkscrew pattern in the jet. And one can estimate the period of free precession if this pattern is due to free precession. And it is actually in around 100 days, I know. So in that same range as here. And so I'm it's very interesting to see an independent support for free precession. There's also, in the radio timing, there are some long-term periodic sort of residuals in that same range. So since I'm not working on accreting sources, the question is here, how sure are we that it is really a free precession, because there is an accretion torque? Is it just not important, or, you know, like, would it be precessing basically the same way if there would be no accretion? Is that the conclusion here, or do you know?
Yeah, I'm not an expert in this, and I actually literally had the same question. So the paper is by Jeremy Heil, and if you want yet another IXPE talk, he gives a really good talk. So,
Okay.
So I'm actually going to refer to you to his Nature Astronomy paper, and I've tried to go through it and ask him directly a couple times, and I must admit I don't quite be. He's convinced it is free precession, but I don't actually quite understand the arguments why you can definitively show it's not due to the torques. Yeah, and that's a very good question.
Okay, thank you.
And sorry to not have a better answer. But no.
Yeah, Manal, yeah, you got a question?
Yeah, thanks, Phil. So when you talked about the pulsar nebula and they having almost maximal polarization, so you mentioned that probably this favors turbulent shocks as the particle acceleration mechanism, and you mentioned magnetic reconnection, but I'm having a hard time imagining magnetic reconnection happening on a very well-ordered magnetic field, because you need magnetic lines twisting and so on. So besides this favoring any models where particles are accelerated in magnetic fields that are turbulent, do we have a better picture for what could actually be the particle acceleration mechanism?
Wow, you guys are all doing it on the questions, which I'm not the expert on. No, that's actually why I say this may power this AGN. We don't really have any. And again, if you want to get into this discussion, Roger or Nicola Bucchiantini would actually be excellent people to pursue this question further. And really, even in our own papers, we just say, essentially, you're right. The results are we exclude having a highly turbulent situation, but we don't have any other indications. I don't have any other, or from IXPE, we don't have any other indications as to how magnetic, reconnection would actually occur. And the one thing that I will point out is you're right that magnetic reconnection is hard when you have a static field, but in this case, we actually know that the field is continuously being regenerated from the pulsar itself, that the Poynting flux is coming out from the pulsar. And I think that might enable reconnection because it's a dynamic feed. Even though it's well ordered, when you look at it instantaneously, it's actually a dynamic situation rather than just a static field.
Thanks, Phil.
Yeah. I think a tricky thing is that you're seeing emissivity, so the field could be stronger in some place. It's not direct measure of acceleration where the particles are emitting, which confuses things sometimes. Any other questions over here?
Well, just a quick. Sorry.
Yeah, go ahead.
Question is about this. One of these first slides you showed for Cygnus X1, and you are talking about possible sites of X-ray production. So, what is the origin X-rays actually? If you are talking about Cygnus X1 or Cygnus X3, like microquasars. So you are talking still about X-rays from distant corona, or there's also could be synchrotron X-rays, right, from the jet?
Well, I'm going to ask Henrik to correct me if I'm wrong. So in Cygnus X1, we're seeing it's an unobscured system, so we're seeing right down. And the result from Henrik's science paper is actually from the hard state. So the emission is dominated by the corona. And so I think it's a standard disk corona sort of thing. And from the geometry, we're then, since the polarization is aligned with the jet, the corona has to be extended. So I think that rules out the models where the X-ray emission, in the hard state of the binary system would actually be produced by synchrotron radiation in the ice of the jet or something like that. Okay, I'll pause in case Henrik
It's actually a pretty difficult question. So, yeah, inverse quantum emission is still favored, and the scenario with this extended, horizontally extended corona is a good one. There's also the competing kind of model that it's still inverse quantum, but it's from these more bigger plasmons instead of just hot corona. So these are the reconnection plasmons. So that's a Biloborodov scenario. And it's also quantization, but it gets compromised by these big plasma blobs. Then Monika Moskowitz, she proposed that it was more like an SSC type mechanism. That seems to describe the data as well. For the synchrotron from the jet, we had this kind of given that it's parallel to the jet and that the flux only contributes 10%, we thought it couldn't be enough to explain the 4% polarization. So I
do you have a?
It's still quite open, probably, and especially what heats a corona and how you get so much energy, even though it's kind of instantaneously emitted. But there's still all these different questions. It's also super odd that then you have these hard state and soft state, and the polarization direction seems not to change much.
But do you have at least one example when could be jet-related X-rays like GRS 1915 or all what you have observed, you refer to the thermal X-rays, corona or disk.
So that's why now mostly what we go with, other than that it's sometimes higher than you would expect, and then you have to invoke some mildly relativistic motion of the corona. So, but we don't have like a strong indication for a jet so far, I think.
Okay, thanks.
Yeah, and I'll advertise Hendrik's and Yuri's talks. I didn't discuss 4U1630, where the polarization is much higher than you can reasonably produce in many models. And then since you mentioned Cygnus X3, I'll also show a slide here on Cygnus X3. Cygnus X3 is very highly polarized. And our interpretation, or the interpretation of Alexandra Veladina from Turku, is shown over here, that we're not actually seeing the compact source directly, but we're seeing radiation that the source is, again, super Eddington, so there's actually an accretion funnel. And in these pictures over here, the yellow would be the inner surface of the accretion funnel, and then the blue would sort of be the outer parts of the accretion funnel. And what we're seeing is emission from the central regions that's then reflected off the inner edges of that funnel. Okay, and so the IXPE results are shown over here, where this is the orbital phase of Cygnus X3. And so the first results were actually from the hard state with the blue triangles, where the polarization is very high, and that's much higher than you can reasonably get from a disk or a corona, really suggesting scattering is very important here. And it changes with the different states. As most of you probably know, Cygnus X3 has a whole bunch of states. And her interpretation is that the geometry of the funnel actually changes according to the state, and also in the amount of material inside the funnel. In the hard state, the funnel is essentially empty inside, but then we go to the ultra soft state, it actually gets very filled. And so in that case, we're not seeing the central object at all. What we're seeing is the scattered radiation coming off the inside of the funnel or from material inside of the funnel. And again, this leads to the conclusion Cygnus X3 is an ultraluminous X-ray.
Wait, what is the intrinsic luminosity for Cygnus X3?
Well, that's so. That depends a little more. What I'm quoting here is the apparent luminosity. The intrinsic luminosity, unfortunately, I didn't write it down. It depends exactly. For that one, you actually have to figure out how. You need better constraints on the funnel opening angle, but it's at least around 10 to the 39 hertz per second.
And 39 is close to Eddington.
Yeah, close to Eddington. Probably,
so even
but we're not sure. So, yeah.
So even intrinsic is close to Eddington.
Yes.
Maybe one question related, have there been any observations of SIG-X3 doing the radio loud huge outbursts where there's probably is a jet and gamma rays come out?
No.
Is there a TOO standing or anything like that?
Well, we actually had a TOO last summer about this, but it didn't. I forget, it didn't quite work in the end. Either the radio outburst failed or the radio flux went down before IXPE could get to it. We do have a, in addition to the geo proposals, we do have a DDT page. And so, you know, for events like that, we actually, if you just go to if you search Marshall and IXPE and TOO, you can find a page where you can make requests. It actually then goes to my cell phone DDT request we up at 2 this morning. So.
Wow.
But yeah, there has been discussion of Mike McCullough, who you probably know from CFA, is very interested in this, and he's the one who proposed a DDT before.
Yeah, actually, we're trying to.
Perfect.
Yeah, we're trying to do that. I actually have in place a VLBA proposal that we'd like to try to coordinate with something like IXPE, because we will actually follow a major flare with VLBA observations for 5 straight days. But we have not observed the really major flares. And in fact, during these observations that IXPE has done, the ultrasoft is very similar to the observation that was done with GRISM in terms of the state. So that was very similar to that. With the other ones, the hard state, there is a compact jet, but in the submillimeter at around 225 gigahertz, you're running around about 100 millijanskis. During the major flares, you can get up well over to 4 to 7 janskis. And there are also big changes in the polarization angle, and they're actually in one case actually a polarized flare that doesn't have an unpolarized response. Otherwise, there is usually a response. But anyway, this is something I'm still trying to work at and try to get done.
Cool. Any other questions? If not, maybe I could ask Phil and Henrik. In SIG-X1 in the soft state, I forgot, is polarization detected? Because we had to talk about sort of reconnection, turbulent sort of reconnection in the corona a couple weeks ago. And there's always some residual acceleration, and that could give the non-thermal tail that goes up past several hundred kV, which might dominate at 2 to 6 kV in the soft state. And let's see.
Yeah, it depends on if. Well, I don't consider the soft state of SIG-X1 to be totally soft, but you can see what the polarization is in that purple state there.
Okay.
Like it's right around 2%.
Ah, okay.
And it was kind of lower at 2 to 4 kV, but then it kind of is almost the same from 4 to 8 or so, I believe. So the polarization at the softest went down a bit.
All right. But the direction's the same, you said?
The direction is exactly the same.
Yeah. Okay.
And so we tried to model it, and we only came up with a model where the spin is super high. And then that gave a lot of reflection, like of the thermal emission and corona emission, everything kind of coming close to the black hole and being reflected, and going around the black hole being reflected. And then you got the right polarization direction. But it requires a really high spin of like 99%, a bit higher.
Wow.
So that's a bit odd that this would be so extreme. And but that was the best we could come up with. Otherwise, you should be dominated by the disk emission.
Yeah.
Yeah, and GX339-4 was observed, I think, in a soft intermediate state, and the polarization there is also a few percent, or it's like 2 or 3%, and it's also aligned with the jet.
Okay. Henrik, the polarization at 2% you said was slightly lower. Is that consistent with like contamination from the disk thermal emission? That's not at 6 kV or not really?
I guess, yeah, that it's kind of partially canceling what there's still like 50% or so of the flux comes from the corona or from this non-thermal, maybe jet, who knows, yeah. But and yeah, so there could be partial cancellation at the lowest energies.
Okay, thanks. Felix, were you asking a question? Yeah, go ahead.
Are all this on the plot objects your targets or just selected targets? Because did you observe only these objects?
All the objects that had, when Linny started this paper almost a year ago, these were the ones we had observed. And there are a bunch more since then, like GX339 -4.
And they are in agreement with this, more or less, of this picture, what you have? Actually, there's no
there's no new results that disagree strongly, that disagree with this picture. Yeah, that's correct. Or with this one, but all the new results are consistent with this one too.
Actually, we should start the discussion now, maybe just more general questions. Maybe I'll start. All you have published, all you have analyzed, all this agrees with your expectations? I mean, probably you had some white paper on, so there are no surprises, or so it's more or less expected?
Now, the pulsar wind nebula, I would say, strongly disagree with our expectations. Several, as Henrik pointed out, some of the black hole systems, like 4U1630, the polarization is much higher. For the accreting, the high mass X-ray binaries, the polarization is actually much lower. And now, I would say probably half of our results do not align with what we expected.
So Phil, can I ask, for the pulsar wind nebula, you said you're seeing something that you did not expect to see. So you're seeing much higher polarization. Is that right?
Yeah. I mean, historically, the only result we had was the average for the Crab Nebula, which was around 12%. Is that correct? And now we're seeing much higher values than that. So
almost 70%. I mean, how many of these systems have you observed in the pulsar wind nebula? You showed the Vela.
Yeah, so we did Vela, Crab, MS15 -52. We've also done 3C58.
Okay.
And we've done one other KES-70, I think KES-75. We did half of it last fall, and we're actually going to do the other half in about a week or so. And then we also did the one in the LMC. 0540.
Yes, this twin of Crab.
Yeah, the twin of Crab. In that, it's much farther away, it's much dimmer, and we don't resolve it well. But the results there, I think, are pretty much consistent with the Crab.
How much time do you have to spend on these, each object? I mean, I guess it depends on how bright they are. And
yeah. Well, yeah. So that's another thing. If you guys write proposals, it's kind of moving towards where the standard unit for IXPE observations is more like a megasecond. Okay, we actually accept a whole lot of proposals that take a whole megasecond. I mean, the initial Crab was 75 megaseconds, but of course, or 75 kiloseconds, but of course, it's one of the brightest sources on the sky. Vela was also pretty short. It's bright, but when we're getting to like KES-75, we did 500 kiloseconds in the fall, and we're going to do another 500 kiloseconds in the spring. So that'll be a megasecond total. And a lot of the supernova remnants are a megasecond or a good fraction of a megasecond. SS433, I think, was 600 or 700 kiloseconds. And the PSRJ 1259 was, I think, 800 kiloseconds. The hope was actually it'd be a little bit more polarized, and we would be able to track the variability of the polarization. But
I think this estimate of 50% is probably true. 50% does not agree with expectations.
Yeah, okay.
And for example, the magnetar, that was really surprising that all the models that Roberto Tavani made were not right. And instead of having like two hotspots, we ended up with modeling it with some bright belly band or so. So for magnetars, it kind of was different. And for the stellar mass black hole, this kind of mismatch in inclination for Cygnus X1, the odd results with a hard and soft state, and the polarization direction not changing. Some much too high polarization fractions. So I think there's quite a lot of surprises, which is good, but
Yeah.
and something really kind of contradicting the standard models, like for example, that the lamppost doesn't seem to agree with the lamppost model.
Yeah, and the magnetar is actually quite striking too. One magnetar in particular, the polarization actually rotates by 90 degrees from the low energy versus the high energy, which might be a signature of quantum electrodynamic effects occurring.
I maybe missed, what about some GRB afterglows?
So the GRB afterglow, I mean, so IXPE also isn't very good at responding quickly to TOOs, and we need brighter sources. So we did do the brightest burst of all time, the boat. Michaela Negro actually led that paper. She's a good speaker too, if you want another IXPE talk. But and so interestingly, we were able to do both the afterglow and the direct emission. In both cases, they're upper limits. They're not really very model constraining, but it was interesting that, so we could do the afterglow, and that was what the proposal was for. But because the source, the boat was actually close to the galactic plane, so there are these dust scattering rings that, if like Swift has lovely movies of the rings evolving with time. And so that enabled us to get constraints on the polarization of the prompt emission too. And unfortunately, they're both upper limits, but it was a target we'd never imagined being able to do.
Maybe a question: are there any plans for key projects, or like for SS433? Maybe it'd be cool to get really high signal to noise observations and map out exactly what's going on and lower the error bars. Is that possible? Does that have to come from the GEO program?
Yeah, well, okay, so we've actually had a very interesting discussion with the senior review panel. So when we converted from the prime mission to the general observer phase, the team here actually argued for legacy projects, which would be like discussed in the community, approved by the users committee, and then we would devote 4 megaseconds of time to that. But the review panel decided that should be actually competed by the GEO program. So we have a large program category. If your IXPE observation is more than 1.5 megaseconds, it gets put in this large program category, and we devote 4 megaseconds per year. The senior review panel was actually really advocating we go ahead and do that. We did so right now, for those of you who know NASA politics, where NASA's doing its senior review of operating astrophysics missions, which they do every 3 years. So IXPE is up for renewal for the next 3 years. And we proposed actually publishing a list of legacy programs. And that was actually well reviewed. So assuming we get extended, we will actually go ahead and discuss with our users committee a list of legacy programs, try to get community input on that, and then actually publish that list before, in advance of when the GEO proposals are due, and then inform the review committees that this is what the community feels important. So if you get, proposals for these, do that. Also, there's 2 megaseconds of DDT time. We used less than half of that in the cycle 1. So we'll probably be moving some of the DDT time actually towards the legacy programs.
Great. Okay, that sounds good. Anybody have any other questions or? Maybe yet another question. There was promise to detect spin effects and relativistic broadening of lines or something in some old XP days. Is there any chance of that happening, or is that a legacy?
Oh, no. So I think what you're meaning is, so if you have lens during rotation around a rapidly spinning black hole, you should actually see the polarization angle rotate with energy because the higher energy photons are produced. So we have a hint of that in one source. And so, but I think that's going to require a really long observation of a bright, well, the best way we can probably get that is we have a transient that goes off and goes into a very bright soft state, and then we look at it, and that will give us lots of statistics. And so I think that's our best shot. In fact, I would like that to be a legacy program. So regardless if we have a GO program, we just go ahead and do that. Do that. And then there are a few sources, there are a few black hole sources that actually stay in persistently soft states. And it might also be worth just devoting a couple megaseconds to looking at one of those.
Okay.
But that would actually be a great observation. So.
Okay, I may have cut off somebody, so if anybody had a question, go ahead. Yeah.
Maybe we can ask you, you have seen our program, right, for next 2-3 months, and we have 2 open slots not filled yet. What you would recommend us, because we'd like to cover this quite comprehensively.
Yeah, I would recommend Raju Ramani to do Pulsar with Nebula or Nicolo.
Yeah. The problem with the West Coast is it's difficult to find a time that.
Oh, but Nicolo's in Italy now, I think.
Well, that's great then. We could try that.
Yep, we could do that.
Because I think that also, given your guys' interest in DEV stuff, that's I think actually the most relevant.
Yeah, we do have a couple of open slots this semester.
Yeah, but that is really very good idea to have possibly nebulae, because as I understand, one of the puzzling things, I mean, so that could be good to know what is going on there.
Yeah, you also mentioned Jeremy Heil. I don't know.
Yeah, well, Jeremy Heil, he's our guy. So Jeremy Heil could give a nice talk on Hercules X1, and also I was actually a little surprised that Yuri is on your program for accreting black holes, because most of his work has actually been in high mass X-ray binaries. And so you might ask, so Jeremy could give a talk on Hercules X1 and the whole set of HMXPs, and Jeremy gives a really good talk. So that would be that'd probably be my second suggestion. Though he's in Vancouver, so he has the same time zone problem. But he could he or Yuri could suggest someone else on HMXPs in Europe probably. Because I think we have a bunch of people that like tuning in. I'm just not.
Maybe one just talk on Cygnus X-ray. Although they have a very good paper, so everything is there, I guess. So probably could not be much more done in this paper, right, for Cygnus X-ray.
Yeah, well, probably. I mean, but yeah, so our Sasha Valadina or Alexandra Valadina, she is the author there. Henrik actually has a student also working on Cygnus X-ray.
Yeah, Nicole is writing a kind of more detailed paper. Could be interesting. Maybe I ask her.
Yeah, even just to general review on Cygnus X-ray, but in addition to the new results, of course, because I understand a lot of things are now new with Cygnus X-ray.
That's Nicole Rodriguez Cabello. I can ask her.
Yeah. By the way, I discovered myself, I didn't know that in 1982, this group, Helming or others, published a paper that there's moving outflow with a speed of 0.3, see more than 0.3. So is what I mean is idea on a micro quasar actually was already there. It was really, I didn't know about that, 1982. And it's very clear they saw, it's not superluminal, of course, that was this Mirabel stuff, but that was interesting. It's very, very clear paper that they saw the outflow with a speed 0.3 C from Cygnus X-ray. And then I saw there's another interesting paper even earlier by Helming in Science called The Astronomical Puzzle Called Cygnus X-ray. So I think that was my interest. We maybe start again, talk about this source. But what I ask, you don't have much more to say compared to what was already in the paper, right? This recent paper. If we ask the
if you ask either Sasha or Nicole, they would have a lot. I mean, Nicole has been doing a comprehensive analysis of all the observations, and Sasha has been working on the theoretical side, so she would actually have a lot to say on the theory side. So. But
Rashmi, now you have more than we have slots, right? Ideas.
Yes, that's great. We'll continue. You know, we need to. Maybe we should discuss it. I think you gave some excellent suggestions, Phil.
Sure.
Okay. Felix, should we close the session for today?
Yeah, I think we just had quite very nice talk and
very nice talk.
Yeah, thanks all. Yeah.
Yeah, and just to remind people that in 2 weeks we have Jaco Fink talking about supernova remnants and IXPE. Please join. Thank you, Phil. Please send us your slides. If you could send it to me by email, we would like to post it. Thank you. All right. Bye-bye.
Bye.
Thanks again. Bye.